My name is Simon McElroy. I'm from Semblent. Semblent is a nanotechnology materials company. We work in a lot of different spaces, from automotive to medical to mill aerospace, but we found ourselves pulled into the pretty exciting world of smartphones for a couple of very basic reasons. There's an enormous economic impact of damage to consumer electronic devices by liquid ingress or corrosion, and it's most felt in smartphones because we all have them. So I just want to show you a couple of pieces of data on how big this problem is right now and the kind of material technology solutions that can be applied to fix the problem, and also what we do in particular. So I want to talk about the economic costs of returns and repairs in the smartphone industry. There's about 1.5 billion smartphones produced this year, looking like it's going to get to about 3 billion units by 2020. So each of these products costs on the order of $200 to $300, sells for somewhere between $300 and $700. So you can imagine just a 1% return rate can have a multi-billion dollar impact. You'd probably be shocked that the return rate's about 25%. So there's a lot of cost to the manufacturers, to the carriers. A lot of that cost is passed on to the consumer, to you and me. I'll show you how that works. So how does this affect the consumer electronic industry? What consumers are demanding, and most importantly, how these issues can be addressed by material technology solutions. Obviously, phones can be redesigned with complicated mechanical design, gasketing, all sorts of very specific mechanical solutions that cost maybe $100 per phone and are very phone specific. So the bigger question is, can we just apply a material either inside the phone or on top of the phone, or a series of materials that make it design agnostic? The designer doesn't have to worry about design rules for waterproofing, design rules for corrosion proofing. They can just build their phone, right at the end, coat the phone, and have a massive economic impact on the return rate. And that is actually doable, and it's done today in very large volumes. So how many smartphones are returned and why? This is Consumer Electronic Association data, the same organization that puts on CES each year. They poll hundreds of thousands of people. If you look at other types of consumer electronic products, from digital cameras to DVD players, they keep getting better and better. The designs get refined, so the return rates go down. But for smartphones, sorry, I can't work my pointer. The return rate from 2009, 19%, up to 2014, 27%. It's getting worse. It's getting worse for a number of reasons. One is there's more smartphones in the market. Number two, the demographic has changed. Initially, the demographic was the business community. It spread out to younger people, older people. Let's just say people are more likely to damage phones. But also the complexity keeps changing. The types of products and components that are put into the phones each generation are not as tested as they should be, so they're much more susceptible to damage. The most cited reason for cell phone return, there's a percentage that people simply return buyer's remorse. They don't like the phone, they return it. But now about 40% of phones break while they're being used. Now, a while ago, not so long ago, consumer sentiment would say, I broke my phone, I dropped my phone, I spilled beer on my phone. Now consumer sentiment has changed. It's saying, I want a better product. I want my phone to be protected from the types of liquids, corrosion, even mechanical damage that I will experience with my phone. And that has changed remarkably over the last 2 to 3 years. Really what it boils down to is there's two main causes of damage. One is mechanical drop damage. A lot of people have experienced this by breaking a screen, but there's a lot of things happen when you drop your phone except, outside of breaking the screen. A lot of things break inside the phone. Liquid ingress damage, so they're about half and half. This is a minimum $10 billion opportunity right now, and that's the minimum, because that's assuming that these can be repaired. If they have to be replaced, it's about 4 to 5 times that. There's a massive industry right now in phone repair, and a secondary industry which is growing called phone insurance or device insurance. You're seeing that with companies like Assurion or SmartTrade. It's about a 15% of us take out insurance policies. Of course, that's not fixing the problem. That's just paying extra money. Smartphones are still most consumer electronic devices, but phones are returned to stores. It's a complex supply chain. Contract manufacturers build them mostly in China. The OEMs are in the US, they're in China, they're in Korea, they're in Europe to a small extent. The carriers will sell you the service plan, but most of us still buy our phones in a store. Which means that the first point of return is Best Buy or Radio Shack or perhaps a Verizon store. At that point, a loop is initiated of, do I fix the phone? Do I replace your phone? It's a costly business. Right now, the data says that about just over 30% of phones are returned within 1 week. That is mostly a buyer's remorse issue. That's not necessarily a broken device. But the biggest concern for manufacturers is between 1 month and 1 year. These are broken devices. These are devices that break while they're being used for one of 2 reasons: liquid or corrosion damage or mechanical breakage. It's a massive cost. So when a phone goes into a repair loop, the minimum cost used to be about $50. It's about $70 this year. The minimum cost to simply take the phone, ship it back into a channel where somebody can take it apart and see if they can fix it, even without replacing a component, is about $70. So that's where the $10 billion cost comes from. Now, if they have to replace your device, it's more like 200, 250. So you get to $40, $50 billion impact. There are indirect costs as well, of course. If you're a store or a carrier, or an OEM brand like Apple or Samsung, and a lot of your phones are getting returned, the chances are the consumer will start to switch brands or switch carriers. Think about a carrier for a second. They don't just make $200 off of you per year, they make $1,000, or in my case about $5,000, because I make a lot of international phone calls. So once they have a contract with you, it's a huge amount of money if you switch to someone else. So it's a big, big problem. And finally, this is CEA data again. What are consumers demanding? Well, this is changing, like I said, from less than half to more than 2/3 of consumers. They want a better product. They don't want just better service or better warranty or insurance. They want the product to work better. That means it needs to be designed better, and in our case, it means we need to include novel materials, in our particular case, nanomaterials, that actually protect against the problems that are causing the returns in the first place. So there's been an interesting trend. I don't know if any of you have had your phones coated, but the industry started by putting hydrophobic coatings on the outside of devices. So the thinking here was literally people would set up stores in malls where you'd bring your phone and you'd get it essentially Teflonated, right? You'd coat your phone, the water would run off. Brilliant solution. Doesn't work. It's a party trick because phones are not diver's watches. Most of the water gets in through the ports. It gets in because of humidity. It gets in because of sweat. A particular company that's talking about removing the headphone jack, you'll hear that it's because of thinness. I can tell you that the biggest sweat ingress place on a phone, just imagine people are wearing headphones in the gym, is right here. Every time that headphone goes in, you're introducing something inside the phone that you really don't want there. So even when the water evaporates, you're left with ionic contamination that doesn't come out. So these models have kind of disappeared, and the companies have kind of disappeared. The reality is you've got to code what's inside the phone, and in particular, the printed circuit board assembly. These little L-shaped or sometimes they're just straight line devices. They have tens of thousands of interconnects. The only other things in there are the screen, the battery, and a couple other components. They have very few places for corrosion to destroy the device. everything happens on the PCBA level. So if you coat the PCBA, in particular, you coat it with something that's not a paint, something that allows you to rework the components later. So there's lots of conformal coatings out there, the paralenes and epoxies, etc. Okay, they'll protect the printed circuit board assembly, but you cannot rework the device later. You cannot get at the components. So the trick has been protect the PCBA, but do it in a way where you're not preventing the phone from being repaired or preventing rework, because rework's going to happen anyway for other components. So the place to do this is in the contract manufacturer. If it's done further downstream, after the phone is fully manufactured, if someone opens the phone, they void the warranty, right? So the best place to do it is in the contract manufacturer. Currently, my company, we're doing about 1 million units per day of coating, and that's growing massively. It's not marketed as such. People are not going out and saying, we're coating all your phones, because of one key reason right now is because if they tell you your phone is waterproof, you're going to throw it in a bucket of water, right? So there's a big difference between economically protecting their business by adding nano coatings or warranting it, right? You're going to see both. You're going to see people market waterproofing because it's a feature people want. It's really not waterproofing, it's corrosion proofing. Right now it's pretty much in stealth mode, but if you think about 400 million out of 1.5 billion smartphones have been coated, it's already big. So what we do is we have a number of different nano coatings. I'll show you kind of the structure. It's a multi-layered coating. Starts from about 20 nanometers, goes up to about a micron. But basically, in essence, this is a very simple circuit board, smartphone circuit board demonstration. On the left, we have R-coated bare copper boards compared to OSP, ENIG, and immersion silver, and this is placed in a very harsh environment, 30 degrees C, 90% relative humidity with large concentrations of H2S, SO2, NO2, and Cl2, also known as a good day in Beijing. So it's a pretty harsh environment, but it's simulated to last 20 years. So very, very simple nano coatings that you can't see, and they actually don't interfere with the assembly or disassembly of the parts, can provide this level of corrosion protection and moisture protection today. If you're familiar with the IP, or the ingress protection scale, sometimes called the IPX scale, there's a scale that basically starts with little drops of water to sprays of water to deep tank immersions. So people will talk about IPX level protection. It's all pure distilled water. So that's great if you work in a lab. The tougher test that's being designed, actually by a pretty large company in Cupertino, is called the Gatorade test. It's called the Gatorade test because we literally started with Gatorade. So it's now a commercial sweat solution. But basically, you take a foam board, you dunk it in a beaker of very, very harsh ionic commercial sweat solution, set the voltage. It's dependent on the phone manufacturer, typically 5 volts. We've done it at 15 volts and run it for up to 2 days, and it has to run the whole time. So there are test boards for this, but you also will run a full phone, and then you take it out and it has to run afterwards. It's a pretty tough test. It's a lot harder than a water spray or even a water dunk test. So this test is being done behind the scenes to weed out the good chemistries from the bad chemistries today. Our process is an RF plasma polymerization process. We actually deposit multiple materials in one chamber. There's other ways to do this, but this enables us to get very dense, very cross-linked. There's no such thing as pinhole-free, but close to pinhole-free materials. We multi-layer the materials, so we take out we took out the impact of pinholes, but we also multi-layered different materials of different properties. So for example, we'll add an adhesion layer, then we'll add a hardness layer, then we'll add a hydrophobicity layer, and we'll repeat. These are all very thin layers, but you actually end up with a composite material that has all those properties, which is completely different to putting down an epoxy or a silicone or a parylene, where you just have a single property of the material. What that looks like is the middle picture. We can see these multiple layers. Typically, we'll do about 9 layers, depending on the manufacturer. But overall, it just ends up being a conformal coating. Although that word is misused, our material is much thinner than a typical conformal coating, but it has to conform to all the surfaces. It's optically transparent, so you can't see it. But it's also soft enough. It can be made extremely hard. It can be made glass-like or even diamond-like, but you don't want that. On the inside of the product, you want to be able to get to the component and remove the component. Let's say you have a bad Wi-Fi chip. You've got to enable the manufacturer to take it out and replace it, and then recoat if they want. So it actually has to be quite soft. A couple more pictures and what 20 nanometers can do for you. 20 nanometers can do an awful lot. Our product started as printed circuit board surface finishes, but really that's a big industry, but not half as lucrative as protecting smartphones. And also will protect against dendritic growth on any kind of surface. And this, of course, is a slightly longer term response. But if you get sweat into a phone and you leave it there, even when the water evaporates, you've created the start of a circuit. And basically, over time, the phone is going to stop working. It's very hard to tell why. So in our case, we prevent against that happening. The other thing, if you're going to do a super thin coating, is it needs to be incredibly dense. It needs to have a very high dielectric strength because it does need to be an insulator. Although it needs to have a secondary property of allowing electrical test. So these products are produced on an assembly line. They're then coated and they're then tested. So the electrical test probes or connectors have to pierce the coating but not destroy the coating. So you need to create both a strong dielectric per unit thickness, but also allow it to be soft enough to not be an insulator to an electrical probe. So 2 different properties in play. Just to give you a sense of the scale, we do develop these in-house in Cambridge University, actually. But they're scaled up to the machine on the right. We'll do about 3 to 4 million smartphones per year. So there's at least 100 of these in production. So it's a very scalable process. And then finally, as you know, it's not that hard to create hydrophobic materials, but most of them contain long-chain perfluorinated chemistries. These are being outlawed across the board. They're being outlawed in the fabric industry, from Gore-Tex, from Nike. They've been outlawed now in electronics from people like Apple. So it's quite hard to create something that's hydrophobic but doesn't contain fluorine, but it's very important to do so. PFOA, PFOS, and long-chain PFCs are pretty much being outlawed from even earphones, accessories. So this is a bit of a difficult challenge, but it's one we've already met. So finally, the economic cost of returns is a minimum 10 billion. It's more like 30 to 40 billion. It's a hidden number that's being passed on in cost to the consumer of the device and also in cost of insurance. But this is now causing carriers, OEMs, and contract manufacturers to lose enough money because it's getting worse and worse that they're solving the problem. Some people like Sony, you're going to see a phone from Samsung in about 3 weeks' time, they will have a mechanical solution, gasketing, very complicated, but it's a one-off solution per phone, very expensive. Most people are going in the direction of applying novel materials, particularly nanomaterials. We're lucky enough to have got in this from the start. And so with that, thank you. I hope it's been somewhat helpful. If you have any questions, go ahead.
What's the impact on recycling?
So the question was, what's the impact on recycling? That's a very good question. Basically, our model as a company is to enable rework, repair, recycle, resell. So what you're actually seeing, and again, I keep referring to one particular company, you're seeing a trend where people are reselling their devices into secondary markets. Because 2 years ago, let's say, Generation X changed to Generation Y. Generation X was almost obsolete. Now the difference between X and Y is very small, so they can sell X into a different market, even the same country, but a different demographic. The reason for technology like this, it will extend the reliability of the device. So people used to not care if it lasted 2 years or 3 years or 4 years. Now they do. If it goes into recycling, if it's into a landfill, it's not a toxic chemical. But really the purpose of this is to enable that repair, recycle, resell loop, which stops us throwing all our phones away every time we buy a new one. Yeah, if it's recycled, the coating will stay, will stay on the component. Yeah, we wouldn't strip it off. There's no need. There's a million other things that are nasty on there, unfortunately. What does it cost? Difficult question, ask what it costs. So it's not much is the answer. So if you take the amount of repair and rework that's done and you amortize it on every phone, it's about $10 to $20 a phone cost today in terms of loss. We're charging much less than $1 per phone. But it's a process, to give you a sense of it, we'll do 15,000 in a batch in 1 hour using pretty simple precursor gases and liquids. So it's really not that expensive. We're kind of charging for the value as opposed to we're not selling the material, we're creating the material in situ, so we can't sell a vial of the material. So we're charging for the solution today. We license the OEM, but we put our equipment into their contract manufacturer. So in some cases it's the same thing. A company like Huawei will do most of its own work, but most have separate contract manufacturers, the Foxcons, Pegatrons of the world. But it's always controlled through the OEM. It's licensed to the OEM. Yeah. Any other questions? Okay, thank you very much.